So Jack concludes that it's not raining. Okay, it seems common sense, but if you put in logic terms, you know, like proof of contradiction. This is an example of proof by contradiction. What's the reasoning? You know, what is the logic? How did that work? Well, so his reasoning. So Jill would be wet, right, if it were raining. Yeah, again, common sense, right? But Jill's not wet. Okay. So let me spell that out. So you're trying to prove the statement P, and in this case, what is the statement P? It's not raining, right? It's not raining. That's your statement P. And we're using proof by contradiction. So not of that, you know, the opposite. Not of it is not raining would be obviously it is raining. Okay. Now, okay, so your not P now is it is raining, and from that you conclude if it's raining, Jill would get wet. Okay, that's your Q. You know, from not P arrow Q. If not P, then Q. Okay, and what's Q? Jill gets wet. But she's not wet. She's just come in and she's dry. She's not wet. Okay, so it's a fact, not Q. You know, Q is Jill is wet. Not Q is Jill is dry. You know, not wet. Okay. Therefore, your not P is false, right? by modus tollens type logic. So your not P is false. So you have not P. In other words, P. You know, two knots they cancel each other out. So you have not P. Well, it's just P. And what's P again? That it's not raining. Okay. So his conclusion is valid. Right. So that's what I'm saying. So so your statement P is, you know, it's not raining. So you start your logic with the opposite, you know, by a contradiction. You contradict P. So in other words, you start with not P, and that would mean it is raining. And then you deduce if it is raining, Jill would be wet. That's your Q. But Jill is dry. So the reality is not Q. Well, if not Q, then by modus tollens, what you started with is false. And what you started with was not P. So that's false. So you have not P. Well, not P is just P. Okay, so you've deduced P. Right? In other words, it's not raining. That's what your P stands for. Okay. Now here I'm spelling out a bit more about this form of logic. You know, modus tollens. I guess that's Latin for mode or method. Or tollens, I'm not sure what that is. I could Google it, wiki it. You can do that, right? But I do know, like, if you have something like if A then B, and you're given A, therefore you can deduce that B is true. So if A is true, then B is true, and you're given A, therefore B is true. That type of reasoning, that type of logic is called modus ponens, P-O-N-E-N-S. Okay? So this is sort of the reverse direction. Modus tollens is when if A is true, then B is true. But B is not true, well then you deduce that not A is true. Okay? So proof by contradiction uses the logic of modus tollens. Right? So that's essential. So to understand what's going on with proof by contradiction, you use this modus tollens. Now I gave this example before. I'll just do it again, a bit of reinforcement. So and it's a bit of soft power. You know, when you teach the course, you choose your own examples. Now I personally do live in Xia, that's Xia. Xi is a sort of like shop or sham in English. So in Chinese, XI is a sh, sh, sh sound. Okay? So shaman. So it's a southeast coastal city in China, not too far, like maybe one night's bus ride south to Hong Kong. So it's not too far. It's damn hot. I don't know if I'll stay here long term. Well, maybe this summer is especially hot. I've found it rather unpleasant. You just had the fan on all day, or the air conditioner. That's expensive. All right. So if you live in Xiamen, you live in China. Okay, it's sort of, you know, if A then B, right? But you don't live in China, so not B. Well, therefore you don't live in Xiamen. Common sense. Right? So hence not A. Right? Now, in terms of the abstract logic, modus tollens, the logic that you're using in the type of reasoning that you're using in proof by contradiction. So you say P is the mathematical statement you're trying to prove. Right? So you're trying to prove P. So when you're using proof by contradiction, you contradict P. You start with not P. And from that not P, you derive, you deduce Q. In other words, if not P is true, then Q. Right? That's sort of equivalent to this. But Q is a contradiction to the fact. I mean, the fact is that not Q is true. So you've derived a contradiction from something that's true, from something factual, okay? That not Q is actually true. So Q is not true, right? Okay, so so the equivalent, if not P, then Q, okay? But not Q is true, therefore not of this is true. And what is that? Well, not P. Therefore not P is true. Okay? No, I don't see this first line at the bottom. Okay, so if not P, then Q, right? But not Q is true. Therefore, this on the left here is false. So therefore, you have not P. Okay, but that's the same thing as P. And so you have proved that P is true. Maybe you can't see the second line. You'll see it next session. I hope you follow the logic of the proof by contradiction, and next session we will do a famous example of a theorem, mathematical theorem, 2,000 years old now. It goes back to the ancient Greeks with a story, and I'll tell you the story as well. So it's a famous example of a proof that uses proof by contradiction. Okay? And we'll do it as an example of this sort of logical thinking.